Okay, quite a large section coming up. High level stuff, chemistry, bonding, and structure. One or two quite difficult new concepts in here, so you might want to watch this once or twice. Anyway, this is what we need to cover. As you can see, there's a lot of information there. You can pause that and have a read of it. Starting though, we're going to have a look at what these stigma and pi bonds look like. So we learned in a previous section about s orbitals and p orbitals, and we said there were 3 p orbitals. We can get these 6 electrons in the p subshell, and our s, there's just one s orbital that can take 2 electrons. So 2 electrons in there, 2 electrons, 2 electrons, 2 electrons. And what we find is that these are able to overlap with one another, these orbitals from different atoms, and form covalent bonds. And if they overlap head-on, so very often if we have 2 s orbitals, if we overlap them head-on like that, we end up with what we call a sigma bond. We can also maybe do a p and an s, or it might be that we have 2 p's, but it's head-on overlap, and that gives us what we regard as a sigma bond. Now, if we have side-on overlap, we get another type of bond that we need to be familiar with, which is called the pi bond. So if we've got 2 p orbitals and they overlap above and below, then this is our pi bond. So in a molecule like this, you'll have drawn this in the past as ethene, and what we've got coming off each carbon, you can see 1, 2, 3 sigma bonds, and then in addition to that there is a pi bond from the side-on overlap of those remaining p orbitals. Now in the other section that we've got to cover, you'll be learning about hybridization, and that will explain to you why we end up with 3 identical sigma bonds and a pi bond coming out of our bonding shape as well. But before we get on to that, we need to talk about something called formal charge. And this is new for this course. Indeed, it's new to me, not something I covered at college. However, it does seem to make sense, and I can see some applications of it. So you can read there what it's all about. We need to be able to work out these formal charges for the atoms in our molecule. And the equation that we're going to use is that one that's listed there. And you can look at some worked examples that work out formal charges. So we start with the top one there, which is ammonia. Ammonia has this structure, NH3. And in it, if we think what would V be, well, V is the number of electrons in our unbonded atom. So nitrogen's in group 5, or 15 I should say. It's got 5 outer electrons, so V is 5. And then we take away from that the number of non-bonded electrons, which is 2, and the number of bonding electrons, which, because it's bonding electrons divided by 2, is essentially just the number of bonds. So we can take 3 off that. And if we work that out, formal charge is 0. If we pick another one down here, they're all going to be 0 plus 1 roundabout. We'll see some examples where they're not in a moment. But if we look at carbon dioxide, which looks like that, carbon, group 14, group 4, it's got 4 outer electrons, so that would be V is 4, take away, there's no non-bonded electrons around that carbon. Remember, we're just working with the carbon atom. See, carbon in carbon dioxide. How many bonds have we got there? Well, there's 4, so 4 minus 4 is 0. So have a look through the other examples and that one there as well. So why is it important? Why are we interested in this? Well, when you get onto the organic chemistry and you start looking at mechanisms and how things react, it's useful in terms of seeing where things will attack molecules. But probably the most relevant application is if you look at maybe this example here. If when you were trying to do Lewis dot cross diagrams, or ones that look like this, you maybe thought, well, I could draw it like this, I can fit all my electrons in there to try and get these octets, but I could equally well draw it like this. Why is carbon dioxide that and not this? Well, we can use formal charge to explain that, and we're looking to have these formal charges at either 0 or as close to 0 as possible. And so drawing out the possibilities and then working out the formal charges, you can see that that one is going to be more likely. Likewise, when we talk about resonance structures, different representations of the same molecule, when we shift some of the bonds around, we can see which is the most stable resonance structure by working out formal charges. And again, if they're zero or as close to zero as they can be, that's going to be our favoured structure. So some examples. So I suggest you maybe give me a pause and then have a go. And assuming you've had a go, you will have hopefully come up with these Lewis structures for sulfur dioxide. So these are possible ways of taking sulfur's 6 outer electrons and oxygen's 6 outer electrons and putting them all together to make a molecule that works for us. This one also exists as a resonance structure. You could have drawn it that way around as well, like that. However, we want to see which of these is most likely, which is the most stable, which is the most realistic. And if we work out the formal charges using the rules on the other page, we find that that's 0, that's +1, that's -1. But over here, all of them are 0. So we'd expect that that would be the actual representation of sulfur dioxide we'd go for. Likewise, if we try this xenon trioxide, ways of drawing it would be like this, or we could draw it with 3 double bonds like that. And again, if you work out the formal charges, this one is -1, it's +2, it's 0, it's -1. Over here though, everything is 0. So this one is going to be our most likely structure. Right, we've been talking in the past about octet rules when we've been working out where to put these electrons and build up our molecules. To look at a few exceptions and a few unusual shapes as well. Now, if we've got beryllium, then obviously that doesn't have that many electrons. It's not going to manage to get up to 8. And so beryllium chloride, BeCl2, looks like that. It's a linear structure, just with 2 pairs around the Be. Some molecules, though, some atoms, are able to go beyond this limit of 8, as it were. And they're able to bring in their d orbitals into the bonding. They're able to mix some d orbitals in, which means they can expand their octet. So if you look at this, instead of having 8 around it, it's got 10 electrons. There's 5 shared pairs. This one has got 6 in it. This shape, I think we've maybe touched on this before, this is going to be called trigonal bipyramidal, and this one here is called octahedral. But they're all exceptions to our octet rule. There they are again, with their bond angles drawn in. And if we start taking away some of these pieces here, replacing them with lone pairs, we get some quite interesting new shapes. So we've got the seesaw shape. If you take off one of the arms, you can maybe, it's a nice diagram this because you can see the extra repulsion pushing these a little bit closer together. If we take off 2 of them, if we've got 5 electron domains, then, and 2 of them are lone pairs, and we're left with 3 actual bonds, we still get that basis of a trigonal bipyramidal, but these are going to repel away. We're left just with a T shape. Here, kind of gone to a bit of extreme here. We've got 3 lone pairs around the middle. All that's left of our original shape is just a straight line, so we describe that as linear. And there you can see 2 other examples. This is quite an interesting one where we've started with an octahedral. We've got lone pairs in the axial positions, in the up and down positions, and we're left just with that flat square bit. So we need to also talk a little bit more about polarity in some of these molecules. And polarity is arriving because we've got uneven sharing of a pair of electrons. And we talked earlier in the periodicity unit about electronegativity. So fluorine is the most electronegative atom. And electronegativity is how strongly an atom pulls electrons towards itself in a covalent bond. So chlorine's more electronegative than hydrogen. So electronegativity increases like that, and it increases like that towards F. So chlorine's more electronegative. It's pulling the electrons towards itself, the shared pair. They're not in the middle, nicely shared. The chlorine's pulling them closer to itself because it's got a higher electronegativity. And we end up with a polar molecule. So this section of the molecule is more slightly negative. That's what that delta sign means. This end of the molecule is slightly positive. Now over here, we also have a more electronegative chlorine than the carbon. But because the molecule is so symmetrical, we find that the molecule as a whole is non-polar. So all of these individual little polar bonds, if you like, cancel each other out. There isn't one area that is more polar than another. And you can say the same thing here. Right, a little bit more on resonance. So resonance from the overlapping of p orbitals. So if we were to look at kind of side on what benzene looks like, each of them has this p orbital on it, and because they're overlapping like that, those double bonds can shift, and so they're of equal energy. Sorry, I disappeared again. Equal energy. And again, some other examples of resonance structures. If we look at this, we deprotonate here. This is ethanoic acid. If we deprotonate, one of the reasons it's an acid is because we end up with resonance structures that gives it some extra stability. So as well as drawing it like this, could be drawn like this. Here we've got nitrogen dioxide, again, two alternative representations. And to kind of show this double bond being in either position, we've got it sort of spread across here. And you might see in some textbooks mention of something called bond order. So bond order, very simply, if we look at this, we could say that the bond order there is 2, bond order there is 1. Here the bond order is 1, there's the bond order is 2, it's a double bond, that's a single bond. What we find, if we looked at a molecule of nitrogen dioxide, is we've not got a double bond and a single bond, we've got 2 bonds that are somewhere in between, and their bond order is about 1.5 each, so they're sharing that double bond as it flips between them. And so their length is somewhere in between a single and a double bond, and their strength is somewhere in between a single and a double bond as well. Also talking about the allotropes of carbon. So carbon in diamond, one of the hardest substances we know, able to make 4 covalent bonds. So to break down the diamond, you have to break this strong network of carbon-carbon bonds. It requires a lot of energy, very high melting point. In these other 2 substances, carbon's only making 3 bonds, which means each carbon has a spare p electron. And we find, particularly with graphite, where we've got these layers, the electrons are able to move between p orbitals around those layers, and graphite's a very good conductor. In between the layers, we've got relatively weak London dispersion forces, and so they slide off one another. And when you're writing with your pencil, that's what's happening. A layer of graphite is sliding off onto the page. Again, have a read of these descriptions. This other example up here, silicon dioxide, not too dissimilar to this in some of its ideas. This large component of sand, using sandpaper, you know it must be quite tough. And again, we've got a network of strong covalent bonds. Okay, so that's what we've covered. Indeed, looking at that, we've actually covered some of the last stuff as well, so useful review. Right, yes, it looks like we have done some of the stuff from the last session as well, so some very good revision. Anyway, thank you for